It's a great pleasure for me to welcome today Professor Dieter Meschede from University Bonn, who is going to talk about the work of Rudolph Clausius. We all know the name, but we really, at least I didn't appreciate how much he has done for the physics and how much of his concepts we are using today. Now, before I pass the microphone to Dieter Meschede, I'd like to introduce him. A little bit from history. I think that we met, I already told that in June 1990. It was my first visit to Max Planck Institute in Germany, when I was absolutely perplexed by how different it was from what we had here back at home. And I was in the group, I was invited by Herbert Walter. I met many prominent people, and among them it was also Dieter Meschede, a postdoc, I believe, at that point, or senior scientist at that point at Max Planck. And in fact, later that year, he became the C4 professor at the University of Hanover, if I recall properly. And since then, I have been following his work very closely, because in early 1990s, his work on that is on micromasers, single atom micromasers, was very seminal. It was an experimental paper, and it gave insight into the interaction between a single Rydberg atom with a single mode electrocavity field, with exchange of photons. So it was very instrumental, and if you look at the papers on theory quantum papers those days, on James' Cummings model, so all of them cited this very instrumental paper. But amazingly enough, diploma thesis of Dieter Meschede was not in quantum optics or related field, or atomic physics, but it was in solid-state physics at a low temperature superconducting area. Why I mention this? Because it's not always that a person has his diploma paper, his diploma thesis paper, to be the most cited paper in the list of his papers. So I think that this sets a standard. You have a paper based on a diploma thesis, and this is becoming your most cited paper. That tells some you about your activities. But later on, he moved from the superconducting domain, solid-state physics, to work at the Max Planck Institute with Herbert Walter, with whom he wrote a paper on Rydberg atom micromasers. Then, after finishing his PhD, he joined the group of Serge Haroche. He moved to Yale, where Serge Haroche was at those years. After that, he moved back to Max Planck, I believe, and under the guidance of Ted Hensch, another Nobel laureate, he defended his habilitation thesis, and almost instantly he got his C4 professorship in Hanover. Anyway, so apart of the physics, like a researcher, he's really very instrumental in our field. He also is interested much in the history of physics and in broader sense, in the broader context of what physics means for the society. And this will be also the topic of our today's colloquium. And final comment, he is not only outstanding physicist, but there are not many physicists, definitely not I know, who are world champions in some of the sports. And he was in 1976. He won the world championship on AIDS, Ossenweslitzer. So he is kind of sports achievements as well. Okay, with this remark, I give the floor, I invite Professor Meschede to present his colloquium talk. Dieter.
Okay. Yeah, thank you very much. It's my real pleasure to be here. So Vlado invited me to give a little lecture series on, I would call it what is quantum, because I consider myself a quantum physicist. And then we talked about this, and then I told him that I have some fascination about the topic I want to talk about here. And so then he said, why don't we make an additional colloquium for you on that topic? And so I hope that I can share this and the enthusiasm I only learned over the past years on this person. The motivation, the reason, as you will see in a moment, is he was a professor of my university, and we celebrated his 200th birthday 2 years ago. Now, before I start, am I better standing here with you or up there or so? No preference. Then I'm stay here because I can walk. I think I can walk. I like walking back and forth, so I can walk more easily back and forth here. So here, since time has a direction, and you all know that there's very few fundamental things that we know, and it's entropy, of course, in the end, which in this case, and associated with the name of Rudolph Clausius, will give us access to the entropy. And so, as I said, my motivation is very simple. We had this big celebration at the University of Bonn about close to 2 years ago, because he had his 200th birthday, and on this occasion I learned more and more things and became more and more fascinated. I would like to try to transmit this idea to you. So here is the time scale that we are talking about. This is where we are today, 2024, and 1822 is when he was born. We see it's 200 years, quite a long stretch. And I'm not going to give a history talk. I'm not a historian, neither of science nor of general history or so. I would rather try to show you that some of the roots, the way we think about physics, are really deeply connected with Clausius and what his impact is in today's world, and maybe where he also failed. Okay, so here is Rudolph Clausius, a picture of him. This was our logo for the 200 years in 2022, and this is when he was born. And he didn't get very old. He became 66 years old and died of a disease which today we would be easily cure with some antibiotic or so. Yeah, but to the last of his days, he was still treating students and discussing with students, at least from what I know from the sources. So there is also we have about 3 times his lifespan, which we want to look at. Yeah. And the idea of my talk is to look into the impact of our scientific ancestors, especially Rudolph Clausius, onto science, onto society, not only on science, and on us in a more general sense. So today, well, we are now 2022, but I take you back roughly to the year 1980. And in the year 1980, in Germany and probably also in other countries, this was the last occasion that you could see things like this. Like that. And let's have a look. Takes about 2 minutes or so. And it's one of the last scheduled train rides. So after this, steam trains stopped in all of Germany or so. Probably here the same thing. High precision measurements. Firing. Okay, so this was one of the last fast trains operated with steam trains, and this was roughly around 1980. And Rudolph Clausius was born there, and now what I want to show you, it's a bit off limits here. I want to show you, by the way, it has a very deep connection to our steam engines, but he was also an early atomist, so this links us very closely to our field of work. So here is now the point with the steam engines. So in Germany, it started in 1785, probably around the same time around here. As a matter of fact, so this was steam engines that were used to pump water out of mines and so on. Yeah, and it was actually also industry espionage from United Kingdom at that time. And so then it went into mobility. In 1980, it stopped here, and we are supposed by the European community, and I think also by general consideration, to stop using coal for making electric energy soon, within the next decades or so. So we have this beginning and we have also an ending, and Clausius is playing a role in both of them. And I would like to discuss that. So Clausius, 1822 born, went to a gymnasium in German on the Baltic Sea, in Swinemünde, I believe. And so he was 17 years old when he made this hand drawing, and this is a steam engine from the time that he was a student in school, before he received the first graduation. You see everything. So here's the firing, here's the piston, and so on. You see regulators for the pressures and so on. It's very detailed, and I think it already shows a bit of the character. This is the technical legacy of Rudolph Clausius is at the Deutsches Museum Munich. And in fact, for the first time in my life, I went to the archive to look at the details of this. It's a very funny thing, very funny experience for a lab physicist to do this and to deal with this. And very clearly, he was fascinated from steam engines from the very beginning. And so my part one will take you into the question of energy and entropy. Obviously, steam engines are there to convert energy of one type into another type. And it's closely related to the time that physicists were thinking of this about this time. So let me quote something that at least for the, I don't know for the younger ones or so, but I'm sure for all the other ones, the Feynman lectures are kind of the standard or so of where we have the high class description of physics or so. It's from 1964, the Feynman lectures on physics, and in this lectures he says it is important to realize that in physics today we have no knowledge of what energy is. And I'm afraid that applies to a large extent till today. And he also says a little later, energy is a very subtle concept. It is very, very difficult to get right. We all deal with energy conservation laws and so on, no problem, and we write it down formally. But to get better intuition is, I think, till this date, difficult for all of us, also in the public. So let's try to do something about it. So, first of all, I'm from the atomic molecular optical community, so, and a quantum optical physicist, and the way different communities in physics also deal with energies or so is a first point in case or so. So, what you really would like to do is, and solid state physicists of course do this, you would always look for, if you want to minimize things, for the free energy typically, yeah? But in quantum optics, in our field, you usually kind of forgot about this. You usually just take the internal energy for atoms and whatever you are dealing with, that's absolutely sufficient. There is not much to talk about temperature or entropy. Also chemists always need this term desperately and so on, yeah? Not we in our community. And this also leads to the fact that there's little knowledge about entropy in my field. And that's this one point. So, where did energy and entropy start out? This will be my first part, historical, but I will give you an indication of how it really in our heads came about also. This is the Magnus House in Berlin. It's a Baroque, you may recognize it's a Baroque house. It's roughly 300 years old or even more or so. And it is called Magnus House because it's named after Magnus. Maybe you know the Magnus. Who knows the Magnus effect? A few people. Among other things, it is the thing that makes in soccer balls deviate from the straight line, yeah? But also other things, and it actually explains why airplanes can fly. Most physicists cannot explain why airplanes can fly or so, but the Magnus explains that. Anyway, he was a 19th century physicist. He was one of the first academic teacher who was collecting his students in this very house, and they made the first kind of what we are doing here, physics colloquium, a weekly physics colloquium. And this was around 1840 to 1850. And as you will see in a moment, Wiedemann, Helmholtz, Clausius and so on were among this group of students. They met each other there, they got to know their colleagues, and this was a starting point for their physics careers. I used to be the president of the German Physics Society, and interestingly enough, I had an office. This was my office for about 4 years or so when I was president. It has a nice fireplace and so on. And there's in case you are in Berlin, there's a very beautiful garden in the back of this. It's the only garden and the only Baroque palais in Berlin surviving, more or less in its original state. So, as I said, this guy, Magnus, he collected these people, young people, at the age of 20, 25 or so. And among them, there was Gustav Wiedemann. So this was late, so you see, this is the late 1840s. He was around 20 years old then. And here's another one, Hermann Helmholtz. He received the von title only later on as a recognition of his things. He was in Berlin at that time, and also Rudolph Clausius. Yeah, and so on the term of energy, the term of energy did not exist in physics at that time. I think most people do not know this, that the way we talk about energy today is not even 200 years old. Yeah, it's 180 years maybe or so old. So the word energeia comes from the Latin region, Latin word energeia, or Greek word here, and it means something like vital activity and potency. If in publications or so there was talk about things we would today relate to energy or so, like Leibniz and others, they would talk about vis viva, which is something close to the kinetic energy today, or vis callida, you can recognize this heat energy then. Yeah? But the word energy did not exist in German language. It was first introduced into the English language. So, and this brings me immediately to perhaps the one absolutely outstanding article by Clausius in the 19th century, which was a bit later, 1865. We will see a few of his life points a little later. But as I said, I don't want to give a historical talk. I want to give a talk on the impact. And I think this is the most impactful, one of the most impactful papers or publications of the 19th century. So I will give you the English translations also here. On various forms of the main theorems of the mechanical theory of heat by Clausius. And so it begins by the entire mechanical theory of heat relies on two main theorems, the law of the equivalence of heat and work, which was the first thing to understand, and the law of the equivalence of transformation, that you can transform one form of energy into the other one. Yeah? And don't worry, I'm not going to present the entire article now in little pieces of this kind. We just look at selected parts. Yeah? One interesting thing perhaps is he showed this to the Naturforschergesellschaft at Zurich. It's like today, he had a lot of trouble in receiving a position. He had to wait for a long time. He wasn't accepted as a professor somewhere. So his first position was at the newly formed Polytechnical Institute at Zurich. Today this is the ETH, the ETH Zurich. And at that time, because it was mostly engineers, it was considered very inferior to universities, like the University of Zurich or so. Yeah. So only a few years later, he then preferred to move from the Polytechnicum to the University of Zurich and then even other universities. Yeah. So anyway, he's one of the first professors at the University of Zurich. And actually, I looked into the scripts of his lectures. It's lecture on steam engine 1, lecture on steam engine 2. So it was very much devoted to engineering also, but because all this was new for physics as well, it was very strong developments in physics. Okay, so he was not the first to think about all this. This is another seminal work in the history of our science. It's by Helmholtz, and it's on Die Haltung der Kraft. Yeah? Here you can see Kraft means the German word for force. And it means, I think I have it here So yeah, it's the conservation of force. It's not force in our today's language, it's energy in our today's language. Yeah? And in fact, also what Helmholtz did in this, what Helmholtz did in this one treaty, yeah, it was 60 pages, and in 1847 he was 26 years old. So look, just I think I can translate for you what this means. So the principle of the conservation of remember the viva, yeah, the ars viva, and this is the kinetic energy. So it was literally the living force is what is called this at that time. So this is the kinetic energy, the principle of the conservation of potential energy, the application of the principle of mechanical energy or so, yeah. Then here, the equivalent of heat, the equivalent of electric phenomena, and the equivalent of the energy equivalent of magnetism and electromagnetism. So in this one treaty, he, I think, got it all. All the conservation laws are written down for the first time ever in his treaty from 1826. So roughly 200 years ago. 1847. 180 years ago or so. So this existed, and Clausius introduces the word energy in this 1865 paper. So this has been digested then by the physical community, by many others, and so on. And so then he says the end. So this is what we just saw, yeah. And so then what happened was in 1849 already, the student Clausius at the student colloquium at the laboratory of Gustav Magnus, this was in the yellow building I showed you, in the Magnus house. He reported for the first time in his life on this work, yeah, on Helmholtz's work. This was shortly, 1849, shortly afterwards. Helmholtz was only a year later. In 1865, in this work I showed you already, he writes on the topic of energy the following thing. This is the German version. Allow me to read it briefly in German. So, hierin bedeutet U die Größe, welche ich zuerst in meiner Abhandlung von 1850 in die Wärmelehre eingeführt und als die Summe der hinzugekommenen freien Wärme und der zu innerer Arbeit verbrauchten Wärme definiert habe. William Thomson, this is Lord Kelvin, hat für diese Größe später den Namen Energie vorgeschlagen, welcher Benennungsweise ich mich als einer sehr zweckmäßig gewählten angeschlossen habe. Here's the English translation. So, number one, this is the way we write this down today in lessons on thermodynamics. I think most of you will recognize this, yeah? This is the heat energy, the differential of the heat energy, this is the internal energy, and this is the mechanical energy a piston in moving up and down and so on exerts, okay? So, and he introduced this way of writing this. So here you can see already where the impact of Clausius is that we use his language till today in teaching. So here U identifies the quantity which I have introduced in my treatise of 1850 on thermodynamics and defined as the sum of the added free heat and the heat used for inner work. Yeah, that's this part. William Thomson has later on suggested for this quantity the name energy of the body. I'm subscribing to this convenient designation also for the German language. So he's the one who did away with all the designations of Helmholtz by Erhaltung der Kraft, conservation of force, and replaced the word force, kinetic force, and so on, by the word energy. And this is not all. In this, we are still talking about the same article. Yeah. Then, just as a side step, I said Clausius died in 1888, and Max Planck actually picked up. Before he went into all the quantum business, he picked up on the work by Clausius. As you see here, this is the dissertation by, this is a dissertation by Max Planck in 1870 at the university in Munich at that time. The principle of the conservation of energy now. Yeah? Only a few years later, the terms are clarified and Max Planck can use this. And there's an interview which I showed yesterday a minute, there's a Max Planck interview from 1942, those of you who understand German can have a look, where he explains this, and he says that when he was looking for his studies, where to go, he said that in Berlin, that Rudolph Clausius really was the most brilliant, one of the most brilliant stars at the sky in physics at that time, that he did want to work on thermodynamics, and this is the clear proof. And I think this education, Clausius introduced the theory of statistical physics to a large extent, and it is this education which in the end led Max Planck also to come up with the ideas of the quantum theory of heat and black bodies and so on. All right, so let us get back. We are talking about the transformations of energy, and so we can transform mechanical energy into heat energy, and that's actually very easy, as you all know. You just have to exert friction, and this is a picture in today's from a contemporary textbook by Joule from 1850. Where he shows how he has measured this heat equivalent. You know, the 4.1 or so kilocalorie or 1 joule or something like that. So he just sets this thing in motion. There's friction on the liquid in there. You measure how much potential energy has been expended here for this process, and then you measure how much has the temperature risen during that time. We do it today in a student lab this way. This is the sketch from Clausius on the very same subject, and here you see this is Joule's publication. Clausius wrote down in his diaries what he had read, and he copied the pictures from these papers. So here you see exactly the same thing in Clausius' diaries, that he digested all this directly from Joule. So again, this is the 1850 publication, this one here by Joule. This is the adaptation in the diaries of Clausius, and this is a 2020 textbook on physics or so. All right. Max Planck later on was a bit skeptic on this because, of course, he does not consider the questions of irreversibility and reversibility in this case, but that's only a side remark here. So, let's go on. We are talking about steam engines, but there's of course more heat engines around, as you know. There's the engines in your car, which supposedly are all to be replaced by electric engines or whatever or so. And there's also the Stirling engine. I think for demonstration purposes, Stirling engine is one of the nicest objects you can have. You can buy many little toys on the internet, and the Stirling engine really shows in a very nice that we just need a periodic process operating between two temperatures, a higher one, the red one, and T1, to continuously convert mechanical energy, to continuously convert heat energy into mechanical energy. So basically what we have to make sure, we need a circular process here, a Carnot cycle, Leipzig thing, or a Stirling cycle, and this moves the piston up and down, and that creates the mechanical energy then, So, and in the case of the Stirling engine, the upper temperature, the cooler temperature is just our surrounding, and all you need is heating from below, and you can do this on a coffee mug, as you will see here. This thing costs about 40 euros on the internet or so. It's a neat toy. So here you see, this is the upper heat reservoir. The lower heat reservoir is the coffee mug, and you see the piston going up and down, and it's driving here this piston. So this piston is just to cycle the gas, the process gas, and the other one converts it just in the heat. And it's true. I have it at my home. I didn't bring it. But if it's running, then you keep it running on your hand for quite a time. Okay. Eventually, it stops. All right. So, we have seen converting mechanical energy into heat energy by friction is easy, straightforward. And now the other way around. So the energy content, so how do we describe it and so on? The energy content of a gas, of a body or so, is changed. How do we change the energy content? This was the formula that I guess you all know from thermodynamics, that Clausius introduced in this form. And so you can either supply or take out internal energy. Yeah, this is the heat energy delta Q. Or you can apply mechanical work. You can compress or you can decompress the system. Okay, so let's look into this. Yeah, here is the Carnot cycle. I should say at this point, so thermodynamics and Carnot cycles are not the favorite topic of many physicists, and even Nobel Prize winners run away when you ask them about it or so. Yeah, but let's try anyway. So how do we convert this? So this is what we call a temperature equilibrium. Yeah, so it's a constant temperature along this line, and in order to so we change for a gas. If we take in this idealized case a gas as a process volume, then we take it, put it into a heat bath. But in order to keep it along the heat bath, when we expand this and extract the energy, the mechanical energy delta W here, then we have to bring in some heat energy from outside. We need to keep it at the heat. Yeah? We will see in the next slide that it's different then. So, but the internal energy is only a function of temperature. That's why it doesn't change here. Yeah? So it means that from the previous calculation, we know that delta Q must be equal to the mechanical energy. So the absorbed heat is fully converted in this idealized case into mechanical energy. And if we take the other process, if we cut it off from the external heat bath, then on the expansion the gas will cool. You all know this, yeah, from your refrigerator and other processes or so. But by the way, the other process around is much better known. When you use the pump on your bike to bring in air, and if you compress the air to enter the Reifen, the carcass or so, then it gets hot. Yeah, not because of your hands, but because you compress, because you compress it. Yeah. So in this case, we can say that the mechanical energy that we gain on expansion must be taken only from the internal energy. Yeah, and with these two, I think, clues, we can construct the whole thing around. So arbitrary processes use the heat bath contribution to create mechanical energy, and also the adiabatic leg to do this. Yeah. So, and for the idealized Carnot process, these two cases are well known and they are well separated. So the trouble is we can only do this once. So we have to somehow close the cycle. Yeah, in order to make this a useful engine, also we need to close the cycle. And what we do then is we switch the two processes. We first go isothermal and then adiabatic back here. And now in this case, we lose energy. Yeah, here we have to take energy in, but now if we compress, remember the pump for your bike, it gets hot and this heat is wasted. Okay, so the process is closed, and then I think you have all heard, so we bring in some heat amount and we lose some heat amount, and we can calculate what is the total amount of mechanical energy gained. The minus signs are just accounting for the proper thing, and then we get the famous Carnot efficiency, yeah, which is 1 minus delta Q1 divided by delta Q2 in this case. And with some calculation, with a little bit of mathematics, you find out that the idealized Carnot cycle is equal to 1 minus the lower temperature divided by the upper temperature. Yeah. And so I think this is one of the most fundamental results in physics. And Clausius was working on this, and he knew all this. Carnot also had been living in the early part of these times, and he was going further steps. Now, one modern thing is also now we're mostly used to machines converting heat energy into mechanical energy, but in these days, because in terms of climate, you will see that climate eventually plays a role. We want to, in many cases, turn this process around. It's not new, but we can run the entire process backward, so we can invest mechanical work and we can pump heat energy from a temperature reservoir, from a cooler temperature reservoir to a higher temperature reservoir. This is of course good for our heating systems in our apartments and houses, because it multiplies the heat that we take from outside by the mechanical work that we invest. And so this is just our demonstration experiment at the University of Bonn. So we have here an electrically driven piston going up and down, and we have two temperatures, and you can measure the temperature on the upper side, which is created by the mechanical heat. And if you, not very far from me, there is an area where many new houses are built, and all of the new houses now have this heat exchanger of the heat pump in the front of their garden, which doesn't make the neighborhoods more beautiful, but perhaps more energy efficient. Yeah. Okay, so here's our Carnot process, and if you rewrite if you rewrite these two equations, you have this equation. And this is what, this was, I think, Clausius' achievement. Delta Q is not a potential function, it's not a state function, it's a process term. And he found that if you divide it by the absolute temperature, then you have again a state function. Yeah, this I think was his great achievement. So Clausius said, let us take this formula, but take these formulas, but replace delta Q1 and divided by T1, then you have this equation. And so to replace delta Q divided by T, which is also called the reduced heat, then you have the entropy. Yeah? And so in this case, in this reversible case, the total change of energy delta S is 0. And so Clausius introduces the entropy using these arguments in this 1865 paper. So delta S1 plus delta S2, if you take one full cycle, in a reversible case is 0. Yeah? Okay, so Clausius recognizes, in other words, when you have this more abstract way of showing it, there is a amount of heat at some temperature reservoir T2, and there is another one, delta Q1, which is running at T1. Then you have your heat engine, and you take out an amount of mechanical energy, which is delta Q1 times eta. Eta is the fundamentally limited efficiency of the Carnot cycle. Okay, and now comes the most relevant question. So, yeah, so this is really the state function, and the entropy S is what he concludes already then is really reigning the world in terms of thermodynamics. It's the most significant and relevant quantity. And the real world irreversible cycle, again here the Carnot cycle efficiency, this is the best possible, it's the best possible thermodynamic cycle. And how can we prove this? With a simple argument along the lines, and Clausius did this all. For this, what we do is we arrange a competition. We arrange a competition. Let's assume that we have another engine, but its eta is supposed to be larger than this reversible eta. Okay? And so this would mean that the delta W to bring heat from here to the upper reservoir would have the efficiency delta Q2, in this case, times this beta superior, okay? If we take the same energy back out again. What does it mean? It means that our artificial heat engine moves the same amount here, but because the same amount of energy up here, but because the eta is better, this means that this delta Q reversible now is, because of this relationship, larger than the delta Q2. Yeah? So, in other words, the combination of these two heat engines, here a classic conversion of heat into mechanical energy and then the heat pump, the other way around, brings, without any other change, heat from here to here. and this is against the second law of thermodynamics. Yeah? So heat flows in this concept without any external action. You can shield this and hide this, then it's away from T1 to T2. And this has never been observed. Yeah? So it's a phenomenological law at this point. It only gets better fundamental justification through the laws of Boltzmann. But this is what shows also the strength of the entropy, this makes the introduction of the entropy really necessary at this point. So, yeah. By the way, so the second law of thermodynamics says heat flows without external action, always from a reservoir with warmer temperatures, a reservoir of cooler temperatures. By the way, there's an interesting thing to this. Robert Meyer, who was the first one to write this down in an article, but his articles were rejected at that time. He was a pharmacist. He had nothing to do with science. I think he was just disregarded in all these things. So he had a big problem in submitting and getting his paper published on this. It eventually did, but he certainly deserves credit for understanding for the first time this in this more clearly formulated phrase, the second law of thermodynamics. So this does not exist, and we need the entropy. So let's come back to so this was just to remind you of what entropy means and how we usually teach it also in classes on thermodynamics. So here is now the essential part in the work 1865 by Clausius. Up here you see in this equation, so there is a difference of the entropies, and you see that he makes sure that the delta Q divided by T is the relevant quantity. It's a potential function. Not Q itself, but delta Q divided by T is a potential function, it's a state function. Okay, so let me immediately go to the English parts. So what he says up here is, he just says again, introduces again the U, and that there is this quantity S, and he says at this point, I suggest to call the quantity S after the Greek word I suggest to call the quantity S after the Greek word entropé, the transformation, the entropy of a body. I have molded the word entropy deliberately as similar as possible to the word energy. So in 1865, he has explicitly invented, he has realized that this delta Q over T is a state function. He has named it entropy, and he has explicitly invented this word entropy together with the introduction of the word energy into the general world in one and the same article. Yeah? So I think you cannot do much more for physics or so. And I think the next part is already the conclusion. Yeah, okay, this is just another thing about this. So we have just looked at this. You know what this means now. There must be some feedback or so. So the second law of thermodynamics, then in the words of Rudolph Clausius, means in a closed system, the total entropy as total has to always increase. And in spontaneous processes can only occur if the entropy S also increases. Yeah? By the way, I think one of the most direct demonstrations of entropy is you just take a drop of ink and let it drip into a glass of water, and it just diffuses or so. And there is never ever the other process around to be seen. Okay, so, and I think this is the simple origin of why we think time has a direction, because entropy has to increase, forced by the action of entropy. Yeah, this is the conclusion of this 1865 article, and let me immediately go to the English translation. So he says, confine myself, that comes with some longer thing, confine myself to stating as a result that if the same quantity which I have called its entropy in relation to a single body is thought of in a consistent way, taking all circumstances into account for the whole universe, and if, in addition, the other term, energy, which is simpler in its meaning, Okay, this is what students feel today. Is applied, the two main theorems of the mechanical heat theory of the universe can be expressed in the following simple form. And here I've left it in German because I think you can, at the very least, guess what it is. The energy of the world is constant, and the entropy of the world tends to a maximum. Yeah. So imagine such a strong statement as the final word in one of your articles or so on physics to be published. Yeah. Just 2 sentences. The world, let me repeat it again because I think it can hardly be topped or so. The energy of the world is constant as a consequence of his investigation. The entropy of the world is leading to a maximum. Yeah. Okay. So one thing I would like to mention here is that he keeps talking about the mechanical theory of heat. And the background of this mechanical theory of heat is that what I mentioned earlier, that I think he is an early atomist. So in physics, when we are in physics, for most of us, I think atomic physics starts with Rutherford, maybe J.J. Thomson or so, around the turn from the 19th to the 20th century. I think this is largely wrong. There was a lot of atomism before. It was not as cleanly shown experimentally, but Clausius was one of the persons who, in my view, had already accepted that there is the statistical world. He was introducing all the concepts of statistical physics already before. Okay, all right. So the unit, the physical unit of the entropy is then delta Q divided by T. It's joule per Kelvin, and perhaps not. It's by the way written onto the gravestone of Boltzmann on the not so far from here, on the Zentralfriedhof in Wien, and the Boltzmann constant, which has the same units as you see here, is now a fixed quantity, and the value k, by the way, introduced by Max Planck also in 1900 only in 1900, the unit was there before, but the name k was given to it only by Max Planck in 1900. And it's one of the 7 units for the new SI system, which we are now using for physics since 2019, also at the internationally agreed units, yeah, for all thermodynamic quantities. And it means this is fixed for all times. Yeah? So it's forever fixed. We will never, in no physical laboratory, measure this again. But if somebody wants to construct a reference thermometer in his lab, he needs to use this by one or another recipe. He needs to use this K value for that purpose. So pour tous les temps, pour tous les peuples, this was the idea of the original metric system in the French Revolution from 1792 already. Okay. So now why is this whole thing relevant for atomism, as I said? Yeah. So what about atomism, and what did Clausius do on atoms, more microscopic physics? We have looked now into the thermodynamic systems. By the way, back up into the 1950s or so, Einstein made some statements that the only physics he really believed in was thermodynamics. Everything else was of a lesser value to him. So let's look at this. So Clausius, as I just mentioned, as you saw, he was talking about the mechanical theory of heat. And the mechanical theory of heat means that the heat is really the motion of all the particles, of all the atomic particles. And this is at a time when there was no idea around of what an atom in detail looked really like or so. Yeah? So, and he at the same time, I don't really prove this here, but he was trying to reproduce these thermodynamic quantities without relation to a model. This is, I think, what intrigued Einstein. Einstein said thermodynamics is independent of the specific model that we are using, yeah, of any physical platform. So, and as I said, it was really my personal surprise when I looked into this a lot more in the past 3 years or so. By 1850 and 60, atomistic models were in widespread use. They were controversial, but they were in very widespread use. And it was driven by chemists, not by our physical community to the largest extent. So let's have a brief look into this, because I think there are some things. Norman Ramsey has written a very important book for the atomic and quantum optics community, which is called Molecular Beams. And I always wondered why in the world did he call this molecular beams and not atomic beams? Because in all his molecular beams, it was only atoms flying through the vacuum. Yeah, I believe I found the solution, and you will see it in just a moment. So, what did the words atoms and elements come about? So, I think I will show you just 4 persons. The first one is Joseph-Louis Proust, who came up with this law of constant proportions, where they saw there is some discreteness in the mass ratios and in the chemistries and so on. Yeah? Then there was Gay-Lussac, who found out that gases react chemically in integer volume ratios. Yeah? So when you have hydrogen and oxygen to react, then you have to multiply the gas volumes to be in the reaction by the same factor or so. It's proportion. And then there was Dalton, and he was able to say that atoms are the smallest. He was the first one to say that atoms are the smallest constituents of matter, and elements are made from identical atoms, and they form so-called compound atoms. So as you see here, as with energy and so on, the terms were not all that clear that were used at that time. And unequal atoms have different masses. Yeah? And as you see, while Gay-Lussac we may consider a physicist, but the other ones we would rather consider as chemists or so. The most important person probably is Avogadro in this respect, who also then worked in Paris. And he had what he called a molecular theory in chemistry, 1811. He was using the Gay-Lussac laws and other things, that this quantity P times V, Boyle-Mariotte, and so on, pressure times volume divided by T is proportional to the total number of points. And then he put in the terms. Yeah? Molecular, by the way, is taken from Latin, and it means small mass. Yeah, moles is mass, and molecular is the diminution form of a word in Latin, and that means small mass. And then he has the molecule élémentaire, this is the atom. And there's the molecule intégrante, which is the elementary molecule, so hydrogen, oxygen, and so on. And then there's the molecule composé, which is today molecule. So today we call a molecule, and an atom. But in that time, and I think extending all the way into the early 20th century, atoms were also called molecules. And I think this is the reason why it has this trace. Okay. So let's go a little deeper into this question of atomism here, the motive force of heat. And this is on the nature of motion we call heat. So he did, and this is now from before this 65, yeah, before this 57, 65, he talked about how heat was made up in a container of gas, containing many atoms rattling about, or many molecules rattling about. And he said, for instance, on the average path length which is traveled during molecular motion by individual molecules, from very general considerations, he came up with the idea of a free wavelength, of a free path length. Yeah, so you know, this is the way we describe it. Molecules have a certain diameter, and we can calculate, if we know sufficiently well the parameters, how long does it take to hit the next molecule or so. In 1856, Clausius did exactly this. He calculated how long does it take. As you will see in a moment, he even came up with reasonably correct parameters for all that. Yeah? So the concepts of a gas and the mechanical properties, the statistical properties were all around, and they were all prepared by Clausius at this time. There's one which I think is really a remarkable thing, and it's worthwhile to be presented more often in classrooms. I think there was another person, August Krönig, who did this also. So if we calculate, if we want to calculate the pressure exerted onto a piece of wall or so by atoms flying around, then what do we need? We need the momentum transfer when the atom hits the wall, comes back, and so on. Yeah, and let's assume a very simple argument. So let's assume all molecules have the same velocity. Then half of them goes left, half of them goes right, and there are two more dimensions. So the momentum is then n, the density of atoms times the velocity divided by 6, flying towards the wall, and they exert the momentum. So the pressure is then just the momentum change times 2m times v, and you get this relationship. Yeah? So there's the pressure, and it relates to, so this is a macroscopic quantity. It relates in this very simple consideration to the density of the particles times the velocity squared. And what I find remarkable about it is that we have two macroscopic quantities, pressure, we know how to measure it, density, you also know how to measure it, and it comes up with a microscopic property, with a microscopic value. Yeah? And so the microscopic value of the velocity of the molecules is extracted from this. Just recast this, the velocity is like this. And Clausius again does this in this 1857 or 8 paper, and so he sees this is oxygen, 460 meters per second, nitrogen is lighter, 490 meters per second, hydrogen, the fastest, has this. It's exactly the numbers we would calculate today, yeah? From this very simple argument. And I think it clearly shows that in his head, he had very much this statistical picture already. So, yeah, another, just, it's a bit out of context, but another interesting thing here is, you know the difference, you know that when we look at the heat capacities or so, we need to take into account the internal degrees of freedom of molecules, yeah, at some point. And so you have this Cp versus Cv ratio, which is 1.4, and the adiabatic coefficients. The adiabatic coefficient is already here. So he says, here one has to conclude that besides the translational motion of the entire molecules, still other motions of the constituents of the molecule take place, whose kinetic energy contributes to the heat. So even without having any insight into the nature of these particles, he realizes there must be something else. Yeah, and by the way, Newton was wrong in calculating the speed of sound from what he knew at that time. So this corrected the mistake by Newton. Yeah. Okay. So yeah, the microscopic theory of gases was here. Let's look at this. And Otto Stern and molecular beams was, again, I want to show you the impact. Roughly, what is it, 80 years later, Otto Stern came along with molecular beams, which again were atoms, silver atoms in this case. Yeah? And this is now 100 years before us. And Otto Stern was, I think, the first one, this is not so much known again. Otto Stern was the first one to show that this statistical physics approach to gases is really the correct one. Before, it was only indirect evidence. So what did he do? Let's have a look at this experiment. I showed this already. This is in my view the most famous postcard in physics. It's the Stern-Gerlach experiment, which I do not want to discuss here. Yeah, so this is what he received the Nobel Prize for. If you want, so atoms are microscopic gyros, and this you may want to call this the first qubit ever or so. The point I want to make is, 1 or 2 years earlier, Otto Stern invented the molecular ray method, and without the molecular ray method, he could have not done the experiment with Walter Gerlach together to find out about this. Yeah. So this is the experiment they did before. It's from 1920. Let me just go very briefly through. It's a rotating device, and so the device has, again, a silver wire in the center, and it rotates rapidly around this. And so it has then apertures here. And as you see, the atoms are ejected from the central wires, and they fly. And during this time, the screen where they are caught is rotating. So depending on the velocity of the atoms are spread out. Yeah? The atoms are spread out. This is indicated here. They do not simply fly straight on a line, but because this is in motion, you can understand this also in terms of Coriolis forces or so. Yeah? The atoms are distributed on this center and on the screen here, on this film. And then you can look it up. And indeed, when the analysis was taken, the atoms, the silver atoms, were distributed across an area at the velocities. I think they had something like 200 revolutions per minute or so. Then the atoms were spread out about 6 millimeters, and this was the first measurement ever on the velocity, on the microscopic velocity of the atom. So something that had been predicted or inferred 60 years before from more indirect evidence. Yeah? And this, I think this entire experiment, together with Stern-Gerlach, opened the path into our modern quantum and microscopic world. And so I think Clausius really has a very, very big influence on this. So here we are, and then, well, I'm not going to talk about this. Then consequences of this, I discussed this this morning. Atomic clocks and Rabi and Ramsey were the consequences of this. And today, the quantum technology, I think, in this way can be well traced back, at least in parts, to the legacy of Clausius also. Not only the entropy and all the thermodynamics grand schemes, but also the microscopic schemes. All right. As I said, one of the important things was molecular beams by Ramsey. Clearly traces back to Clausius. I just want to give you one example of what we do today in our own lab. Not today, it's 20 years ago, almost more than 20 years ago. This is single atoms, and so this was one of our first answers when we control single atoms. This is a laser beam, it's a standing wave of a laser beam, and the atoms are, so to say, attached to the maxima of the standing wave of the laser beam. And if you detune one of the laser beams by a hertz or so, relative to the other one, then this whole thing is set in motion with one half wave per second or so. You can detune more widely, then it moves more rapidly. Yeah? And that's the cartoon on that. And I think here you will see also a real movie. So there are 3 atoms. It's a little bit faster than reality. You see here the time elapsing. Eventually we lose them because the vacuum is of finite size, but it's good enough to have atoms stored in this very shallow lattice containers for about a minute. So I think this is one of the origins of where we started to be able to do quantum processes with single and individual atoms. Yeah? So what I wanted to make is I wanted to really span the frame from Clausius and his thermodynamic work into the statistic world, all the way into our today's world. And maybe you see why I have become fascinated with this. A few words to finish on the life of a 19th century professor of physics in Germany. And so here is just a wrap up. The details are not so important. This is where we show that we had this picture on the steam engine as a student. He was a student in Berlin. He studied, for instance, not only with Magnus, but with famous mathematicians such as Dirichlet. He didn't do his PhD in Berlin, he went to Halle. The reason was, in Berlin he would have had to submit in Latin language. In Halle, at that time, he was already allowed to submit in German language. And the subject was scattering of sunlight on the Earth's atmosphere. So the natural environment has always attracted him quite a bit. Then, as you see here, so 1855 is when he became finally a professor in Zurich at what is now the ETH, but which, as I said, was less prestigious by a large gap than any of the universities. He became a professor at Zurich and then at Würzburg very shortly, and then he went to Bonn, where he spent the final 20 years of his life. And he also was once rector of the university for a year. And my final slide will be about one of his actions as a rector of the university. So here's some pictures. This is the grave of Clausius. When I went there, he is on many cemeteries. I'm sure you have this here. There's the list of famous people buried there. He is not among this. The city of Bonn we just saved it from being, planarized or so, yeah, from being taken away. And the university is now taking care of the grave or so. It still exists, in other words. And this is his house where he lived. The house must have been nicer before the war, because when it was destroyed. But see who the 2 persons were who lived in this house. So Rudolph Clausius died in 1888. His successor was Heinrich Hertz, and he moved into the same house. And so it's in the center of Bonn. and very nice, very close to the main station. I mean, so in these days we all have online access to all publications, or to most of the publications around. Yeah, but even when I was a student, we would have little postcards, and we would, if we wanted a paper by somebody, a reprint, we would put a stamp on the postcard, put it into the mailbox. Please send me a reprint of your paper. Yeah, and I think only the older ones know this still. And from Clausius, we have a huge collection of these reprints from his colleagues, and it's quite interesting. So you see, he noted down whom he sent this to. Yeah, he took very much care of showing, or at least remembering what he had done. So let's look at a few here. So who do we see here? Bertrand Bernier. Is there any famous person in here? On the next slide, I will have some. So Royal Society, when some Siemens became some Tyndall, yeah, Thomson, Joule, Brown, and some others. Yeah. So, for instance, here, and if you look through more closely, then this is a who is who of the science of the 19th century. Yeah. So, oops, sorry. Let's go back. Here it is again. So it's really, as I said, a who is who of the 19th century. So this was this must have been in 1868. The Nobel Prizes were not around before 1900. And so already 30 years before, he was dealing and having conversations with many of the later Nobel Prize winners also. There were also famous mathematicians, famous chemists, and other people. So you know Kirchhoff, Helmholtz, Gibbs, also across many countries, all the way into the United States. Thermodynamics here, Tyndall into Ireland. I think with Tyndall he was a very close friend. They were godfathers of their children or so. And Becquerel in France and so. Anyway, so what you see here is that there was really a very widespread community. The equivalent, the next slide shows the equivalent, I think, of the Nobel Prize in the 19th century, which he indeed received. It's the Copley Medal by the Royal Society. So in 1879, Rudolph Clausius received this. Today, the gold value is 25,000 pounds just of this medal or so. Not so bad. And so you see other recipients. So Gauss, Faraday, Charles Darwin. Then here some of the British people, Joule, Lord Kelvin, here Kekulé, Stokes later on. And Einstein later on received it also. So I think this Copley Medal is also shows the international recognition that to physicists was given already at that time. And the Royal Society was probably the prime institution to do exactly that. So I'm coming to the end, sorry for being a bit long. So honoring the legacy of Rudolph Clausius, I would like to show you a few final things. Here's another paper. This is from sorry, I'm sometimes hitting the wrong button here. I'm sorry. Here it is again, even one further back. So here's another paper from 1881. Yeah? Actually, most of these papers are free access also now, but even though, since they are in German language, they are not so valuable, I guess, for you also. But so this is, I think I have it also in English. No, sorry. Oh no, oh yeah, here it is. On the theoretical determination of the vapor pressure and the volumina of the vapor and the liquid. This is one of the central equations for climate research and climate modeling in 2021. And it again goes via the Clausius-Clapeyron equation back to Clausius. Yeah? The temperature depends on the saturated vapor pressure. It just tells you if the temperature rises, you can have a lot more liquid in the atmosphere, and the rain will be heavier or so. Yeah? And okay, let's not go in this any deeper. And just if you look at the IPCC reports, then I didn't do this myself, but a colleague of mine did it. So in this chapter 8 on water cycle changes, you can do it even globally or so. You can just ask your Google or so, how often do you find the word Clausius? More than 10 times mentioned already in this. I don't think any physicist is more often mentioned in this business than Clausius or so. Yeah. And let's go on. He was, for decades, his books on here, the potential function and the potential, mathematical physics. In Germany, he is considered the founder of theoretical physics, and probably worldwide, he's one of the real founders of theoretical physics. Before, physics was not divided that much. Maybe it's actually I'm not sure it's a good idea to divide physics in theory and in experiment. But apart from that, I think he needs to be considered one of the founders. And his textbooks were the standard for decades in physics teaching, among others by Max Planck and so on. Yeah? Here is the attempt to summarize his impact in science. Here is his lifespan. And so what were his grand deeds? There was one thing, is this molecular theory of heat, which ended up in the physics of the atmosphere and statistical physics. Certainly a very large thing. Then thermodynamics, the entropy. And the entropy, as you hopefully all know, is of extreme relevance in information theory, in life sciences, also in the economic sciences, and so on. So very broad impact here. The next thing was the virials. The virials are just averages of certain quantities of energies or of spatial distributions and so on. And they have influenced astronomy and cold atoms. So for instance, virial theorems, when you look at galaxies or clusters or so, you can take virial theorems and try to find out whether the motion according to the virial theorem agrees with if you just assume classical gravity, or whether you have to assume additional forces. Fritz Zwicky in 1935, I think, is one of the first who was talking about dark matter, and he used Clausius' theorems to find out about the motion of systems in stars or so. He also worked on electrodynamics, but in this case, I think he died. I think he was a supporter of the Fizeau theories of the of the ether theory, which then all this was overcome by Einstein. So I think he was on the path to do something, but he died in between, and so there was no way for him to continue on, and he was probably on the wrong track from today's perspective. But I think it shows that his legacy really extends across, I would say, almost all fields of physics. Yeah. And he's one of the really grand scientists of the 19th century. Clausius and authorities. Authorities in 1870, 1880 meant we had a feudal system. Still, Germany was a monarchy, and Clausius was in direct contact with the monarchy. This is my university, University of Bonn, was founded in 1818 because then at that time, after the Vienna Congress, it was the area where I live and where Bonn was annexed by Prussia, and Prussia founded this university. By the way, it's one of 3 universities which were founded at the time after the concept of Wilhelm von Humboldt, not Alexander von Humboldt. Yeah, the brother was the one who founded the university. It was Berlin itself, Breslau, now Wroclaw, and Bonn. And so it turned out then the university was rapidly very successful, and the noble families of the German states, not only of Prussia, would send their children preferably to Bonn as students or so. So did the Prussian emperors and family, and this is the later Wilhelm II, who we are not very proud of, but he was a student there, and he was a personal student of Clausius. So Clausius was the personal teacher for Wilhelm II with physics. I looked into so as I said to you, I went to the archive and I looked into his scripts of the manuscripts for his usual lecture, and he also wrote another script for the lecture to Prince Wilhelm. He did not spare him. He did not make it easy for him, yeah, I have to say. I don't know how this guy in the end performed. But at least Clausius tried to educate him in the very same spirit he was trying to educate all the other students. He did not Clausius did not live up to the time when he became the emperor. This was in 1888. Clausius died the same year, shortly before. This was his grandfather, Wilhelm I, or William I. And he was a rector in 1884, and the University of Bonn and other universities, probably here, Habsburg universities would also do this, they celebrated the birthday. They typically celebrated the birthdays of their emperors. Yeah? This was on March 23 every year. So the university had to get together, make whatever festivity for that. Yeah? And this is now my last, almost my last slide. I will just have one more quote. On one of these occasions now of these festivities in 1885, Clausius gave a speech, and he had this speech written down and printed. And this speech, and this is, I personally find absolutely mind-boggling, and if anybody is interested, I can send you the English translation, which my secretary did in a wonderful way of this. It's an address on sustainability, 140 years ago. And so let me finish with this. So the title of this is about nature's energy reserves and their utilization for the benefit of mankind. And so in this public address, here is the quote: "The power sources of nature were made available to man in a way never imagined before." Remember the steam engine, yeah? "The following centuries will have the task of introducing a wise economy in the use of what the sources of power in nature offer to us, and especially of not squandering wastefully what we find in the soil as a legacy of earlier times and what cannot be replaced by anything." This is a very strong statement, and remember, it's 140 years old in front of a university public or so, and not only university public. So, this is my final slide. I wish you, as the participants of this colloquium, successful and enjoyable springtime, and perhaps finding support for the introduction of a wise economy in our societies in Europe. Thank you very much.